So what we're going to do here, before I actually introduce the concept, let's play a guessing game. Now, what I'm going to do is I'm going to show you 18 sequences of coin toss generated by 3 types of coins. There are fair coins, which by its name, it has half chance of coming up heads and half chance of coming tail. There are double-headed coins, which always come up heads, and double-tailed coins, which always come up tails. The exact ratio of them are unknown, so it could be all fair coins, all double heads, or all double tails. But to make the problem easier, what I can already tell you is there are as many double-headed coins as double-tailed coins. So then so you could go from there are only fair coins, so there are no double head, no double tail, and at most you could have 9 double heads and 9 double tails, right? So this is to make your task easier. What I want you to do is to guess the number of fair coins based on the draws you see, right? So the number you guess should be from 0 to 18, right? There might be no fair coin, or there might be at most 18 fair coins. So you just need to guess one number, despite there are 3 types of coins, because I already told you the 2 extreme types have the same chance of occurring. Okay. Now, I generated numbers with a random number generator. Obviously, I didn't actually flip coins, so I just used Excel to generate the numbers. But I want you to guess, and every time you guess, I want you to write it down somewhere. Just to take a look, to think about how would we estimate probabilities as humans. Okay. When every time I pick the back button, it would just have gone. I hate this part of recording with PowerPoint. Never mind, at least it doesn't actually affect anything. All right, now here's the second game. Imagine you have a fair coin and you are generating a sequence of draws from it. Just imaginary, you just imagine you're flipping a coin. I want you to write down, imagine yourself flipping a coin. What would be the first outcome? Is it going to be head or tail? Write it down. Now write down your second draw. Then your third draw. And your fourth draw. So we're going to just write 4. Okay, just going to write 4. What do you see? Now, these kind of things don't necessarily work within class this small. We use so when we have more students, it usually makes more sense. But okay, so let's talk about the motivation before we come back to what these games are about. Now, we have been talking about analyst recommendations, adding value only when the asset has good underlying characteristics, and that trading costs will erode any profit following recommendations. And what we're going to talk about now is why might analysts be over optimistic in their forecast, and why might investors be too willing to believe in analysts and fund managers' ability. Now, fundamentally, when analysts' task of making forecasts is not that much different from an investor choosing a fund manager, right? In both cases, you're kind of looking at past data and trying to figure out what to do or what would happen next. When you choose a fund manager, you're implicitly trying to make a forecast of how well the fund is going to do. So in that sense, you're just doing an analysis as an analyst would do. So DeBord and Thaler, 1990, do security analysts overreact in AER paper and proceedings? So it's using IBIS data, same data we have just used. They look at earnings per share, so they're not looking at the consensus forecast, they're looking at another part of the data, the earnings forecast. All right. So what do we see here? What do we see here? Now, what they're looking at is what happens when you regress the forecast on previous forecast? How likely they're going to revise? Okay, so equation 135, regress actual earnings per share change on forecast earnings per share change. So if you have when you're regressing a number on another number and the coefficient is more than 1, that means the dependent variable change less than the independent variable. So a coefficient is more than 1 in this case would imply that the earnings per share change is smaller than what the analyst thinks is going to happen. Right? So 1, 3, 5. Okay. Actual change regress on forecast change. So they have different durations. I think it's 1 month, 2 months, and a year. Okay. So constant term. What we want is to look at the slope. Slope. What you have is 0.648, 0.459, and actually this case is actually very close to 0. Right? What you suggest is actual change in earnings is smaller than the forecast change. So analyst predicts that the company is going to earn a lot more money, but then on average, companies do not actually reach the analyst's predictions. Furthermore, if you look at very long duration, then the forecast earning change almost have no predictive power. The guess is pretty much useless. Equation 246 regress forecast revisions on forecast change. So when an analyst makes a recommendation in January, she can revise it at a later date. What's the relationship between the revision in a later date with the initial forecast? So a negative coefficient in this case means that a positive forecast is more likely to be followed by a negative revision. So if I predict the stock is going to do very well, if I predict the company is going to earn a lot of money, the more rosy my prediction is, the more likely I have to revise it downwards. That's what this would mean. So 2, 4, 6. Once again, the coefficients are negative 0.181, negative 3.81, and negative 0.439. So this, as explained, means that more rosy predictions are followed by more negative revision. And unlike the relationship between actual earnings and forecast earnings, in this case, the effect is actually stronger the further you look. So if I predict a company is going to do well in 5 years, very likely I would have to revise my estimate downwards in the future. So it looks like, on average, analysts give predictions that are too exaggerated, right? I predict there will be a big change, but turns out there isn't one. I predict the company is going to do very well, but I've realized later on that I'm actually too optimistic, so I have to revise my estimate downwards. In both cases, it points to exaggeration of prediction. So do people believe in analysts? Now this is an advertisement I screen capped from Yahoo Finance. And you have this guy wearing a clown hat, and he is actually an analyst. A supernova is when a star explodes and the bursts release tremendous energy. And of course, supernovas are rare and only take place if certain conditions exist. And the unbelievable return of the Motley Fool co-founder and supernova team leader David Garner has directed his readers over the years from Amazon, blah, 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 to very high return. That's what he wanted to say, okay? And so what evidence did he cite? David's total average returns in Motley Fool's stock advisor since March 2002 are 160% compared to 25% for S&P over the same period, and his total return in other recommendations since October 2004 are 59% compared to 16% for the S&P over the same period. Now, what this shows you is past return is what people use to judge future performance. You have all heard the disclaimer that past return does not guarantee future return. And we have already seen evidence of that. Momentum. Past return guarantees return maybe in the future a few months. But beyond like a year, there's absolutely no meaning to follow past return. Right? But people certainly very like to quote like 10 years, 20 years of return and say, well, you know, I've been doing very well cumulatively in the past decade. So trust me, I'm going to do well in the future. Right? So that's what people do. And what we're going to investigate today is what have behavioral economists and psychologists found out about how people interpret past data. Okay. Now the question central to what we are talking about is how much information can one infer from a small sample, right? Suppose you have run an experiment on 20 subjects and have obtained a significant result which confirms your theory, right? Set the C statistics is 2.23, p-value 0.07 and 0.05 in a two-tailed test. Good, right? Now, if you have learned statistics, then you know a p-value below 0.05 is a good idea. As you learn more about statistics, or if you start reading more about what statisticians have been saying, then this criteria is actually very bad. Like, we shouldn't be using p-value so much. But nevertheless, it's the norm in many disciplines. Is to say, well, if you have a p-value small enough, good. Now, if you have cause to run an additional group of 10 subjects, what do you think the probability is that the result will be significant by one tail test separately for this group? So this question is actually asked by Kahneman in a conference for psychologists. So 89% of the respondents indicated, well, there's an 85% chance I think we're going to get significance in the subsequent 10 subjects. 11% says maybe we should, like somewhere around 50% chance we're going to get significance. And the true value is about 47%. So when you have 20 subjects and you get statistical significance, if you rerun it, there's a good chance you're not going to get statistical significance. And you think about the way that t-statistics work, that's just natural. That's just natural because your average, your estimate, your sample mean moves around, right? Depending on your sample. In your current sample, if it's right at the point where you get significance, 0.05, like 5% chance, right? Then there's pretty much an equal chance that you're going to either be over or below significance the next time, right? Intuitively. Because then if the number, the sample means is moving about randomly, and you're right at significance this time, the next time it could be either over or below significance with about equal chance. So that's why the true value is pretty much 50%. But then, as you see, most social scientists probably don't understand that. I bet you don't understand that, even if you're taking statistics, right? Unless it's explicitly mentioned, you might not have thought about that. That significance in one sample does not guarantee a very high chance of significance in the next sample, right? Which is why statisticians have been saying that the use of p-value is so bad. Is that it gives you a false sense of confidence. So you have a p-value smaller than 0.05. You have been taught that that means there's only a 5% chance that this could happen. It would make you feel like if there's only a 5% chance it could happen, like I'm guessing there's 85% chance the next time it will still be significant. That seems already very conservative, right? But no, what it says is there's only a 5% chance it will happen if the null hypothesis is true. It's not the same that say that. It's not the same as saying that that's the chance you're gonna get in significance in the next test, right? So it's quite clear that even social scientists, somewhat trained in statistics, don't understand how probability works. Right. And so what evidence suggests is that people believe small samples have to resemble the underlying distributions. Now, to generate a sequence from the ECON game I asked you to play in the very beginning, this is actually a study conducted and published in Psychological Review, Randomization in Individual Choice Behavior. This is the second game. Sorry, this is the second game. This is the second game asking you to pretend that you're flipping a coin. And so this is published in Psychological Review. And what do you see? Now, if it's a truly fair coin, what we had, when you ask enough people, roughly you should get 50-50, right? 50 heads, 50% heads, 50% tails. And remember, this is supposed to be an unbiased coin. So you see this, but yet you see a slight amount of negative correlation. When the previous side that people wrote is a tail, they are more likely to tell you a head in the subsequent round. It's like 60% chance. This one. But that's not bad. That's not bad, as you see. Now, if after 2 rounds they wrote heads and tails, then there's an almost fair chance that you give you a head. Okay, good point. But what if it had tail after 3 rounds? Then the ratio goes down to 38%. Now this coin doesn't look very fair anymore, right? And if it's like head, then you only have a 30% chance. So how do you interpret what's happening? People were asked to flip a fair coin in their mind, yet based on their behavior, it's anything but a fair coin. What do you think is happening? Now, intuitively, if you actually write down a series of heads, do you feel like it's a fair coin? You don't feel like it's a fair coin, right? What feels like a fair coin? A fair coin feels like heads, tails, head, tails, head, tails. That feels like a fair coin. But in fact, that would not be a fair coin. That would be a 100% negatively correlated coin, right? An actual fair coin means that there's a 50% chance head would appear in every single round, and that would inevitably means you sometimes get all heads. So subjects are clearly not generating a sequence with IID fair coins. And one thing that we observe here is that people simply, it's very hard for people to imagine that rare events would happen. Something like heads would happen. Even though, like 3 heads in a row happens 1/8 of the time, right? So, and before I go on, so what about the game I asked you to play in the very beginning, the 18 coins game? It's actually a part of the dissertation of one of our MPhil students. Actually, no. It's part of one of our MPhil students' undergraduate senior thesis. He ran this experiment, I think. And what about those coins? So actually, all of those coins are fair, every single one of them. But as I said just now, with 18 fair coins, you would see something like you should see something like 2 double heads. You should see what looks like 2 double heads and 2 double tails, right? You would see for a series of 18 fair coins, 2 of them would show you heads for all 4. Something like, actually, no, okay. I show you 4 rounds of coins, I think. So if you, with 4 rounds of coins, you would see 1, I think, 1, right? Because the chance of 4 heads coming up in 4 rounds is 1/16, right? 1/2 to the power of 4. So you should see at least 1. And the chance of seeing similarly an all-tail coin would also be 1/16, right? So the fact that you observe a series of heads or a series of tails in such a small series of data doesn't really tell you much about the underlying distribution. But this is something that people have a very hard time of understanding. If someone wins like in lottery or in horse betting 3 times in a row, or soccer betting, right? If someone managed to bet on the right team for 3 times in a row, he's probably going to be worshipped among his friends. So it's very hard for people to understand. So the law of small number gets its name from the law of large numbers, which you should have learned, which says that sample mean converges in probability to population mean. So what it says is, if you have enough draws, chances are you would see the sample mean would be the same as population mean. But then once again, it converges in probability. It doesn't say that at a particular instance it will be the case. The law of small numbers says that the belief that a small sample mean should resemble the population mean to a high degree. So people think that they should see 50% heads and 50% tails even in 4 coin flips. That would be a belief in law of small numbers. Right, so can we come up with a model that explains the behavior we observed in the studies we mentioned? So a few things we have mentioned. So first, people are very quick to make judgment on the underlying distribution. Okay. When you ask them to try to come up with a fair coin, they come up with something that doesn't resemble a fair coin, but more something with negative serial correlation, right? Can we come up with a model that explains that? And yes, this would be, so we have so this is the model of law of small numbers. It's actually quite simple. They use some Bayesian, use the Bayes rule. So but it's very simple. So we're going to assume they're just binary events, right? So A and B, like heads and tails, with probability of A equals to theta. Now, the underlying true process is IID, but the decision makers mistakenly thinks that it's made out of a draw from a fixed number of A's and B's without replacement. This is the key, without replacement. So think about what that would happen. For example, let's say there are two A's and two B's, right? Initially, you have half chance of getting A's and B's. But after a draw of A, you have removed one A, so you're left with one A and two B's. So the next time, the chance of getting A's is only 1/3. That's what it means. So this would capture the phenomenon observed in a generate a sequence from a fair coin game, right? When you ask people to mentally generate the series of coin flips that are supposed to be fair, what they have in mind is not IID. What they have in mind is something like this. I have like maybe 10 fair coins, I have maybe 10 heads and 10 tails. As I draw, I'm drawing down the heads and tails accordingly. So if I come up with many heads, then I'm left with very few heads in my imaginary bucket. So the next time I draw, a tail is much more likely to come out. So since, as I said, this model uses the Bayes rule, so there's a pi-ra, so that's pi, okay, and the decision maker updates his belief according to the Bayes rule. And for trackable reasons, we just assume that the decision maker resets the number of A's and B every 2 rounds. This is just for mathematical simplicity. It gives us the insight we want without complicating the math. So let's take a look. What we mean is that we start off with AABB. You draw an A out, you're left with ABB. So in the second round, when we ask the individual again, okay, what's the chance of getting an A? 1/3. What's the chance of getting a B? 2/3. Right. Now, so let's say you draw another A. In his mind, according to the way we formulate, right, we'll be left with no A's. Even though he supposedly knows this is a fair coin. To avoid this problem, you're going to assume he's going to reset it at some point, so that he's just going to build it up again later on, and before he draws it again. So once again, this is mostly for trackability reasons, right? Otherwise, at some point, he runs out of coins. And when he runs out of particular type, then it's not very clear what would happen in his mind at that point. So we reset the numbers. Okay. All right, so an example would demonstrate how the model works. So suppose an investor believes that there are 3 types of fund managers or analysts. There are bad ones, the average ones, or the good ones. Bad manager outperforms other managers 1/4 of the time. Average manager outperforms half of the time. And good managers outperform everyone, say, the average by 3/4 of the time. And the pi-ra is all 3 types are equally likely. So after one successful year, what's the chance that a particular type of manager will succeed again? if the individual is a Bayesian. All right. All right. Okay, let's take a look. So the Bayes rule works in okay. Now, assuming that the underlying distribution is actually IID, right? Is actually, so what do we, so what, okay, what do we have? One successful year. Okay, so what we have is something like this. Oops. Okay, so probability that you get a successful year after another successful year, and the manager is actually a good manager, right? If the underlying distribution is IID, then it would be just 3/4, right? And if it's the average manager, then it'll be 1/2. And if it's a bad manager, then it would be 1/4. But what if you have this wrong belief that the likelihood of success comes from a bucket of success and failure, like this, right? So let's say everyone have two draws of success and 2 draws of failure, right? And then you draw a success, so you're left with 1 success and 2 failure. So what if this is the logic here? Now in this case, let's think about it. The good manager has 3 out of 4 chance of succeeding. So the P success, given that he's success and good, equals to what? Well, he has 3 out of 4 draws being success. He draws 1 out, so he is left with 2 out of 3 remaining draws. What about success? After a success, and the manager is a bad type. Oh, sorry, it's an average type. The average manager has 2 out of 4 draws that are success. He draws 1 out, so he's left with 1. So he's only have a 1/3 chance of succeeding in the subsequent year. And finally, if it's the bad manager, he only has 1 out of 4 chance. He has already used that up, so he actually has no chance of succeeding. If you take a look what happens here, first you should notice that if people have this type of thinking, they would underestimate how likely a series of events is going to happen, right? Across the different types, no matter whether it's good managers or bad managers, the decision maker simply doesn't think it's likely that one successful year is going to be followed by another successful year, regardless of type. However, the underestimation is a lot more severe for the bad types, right? Because if I already think that it's unlikely for you to succeed, and you did succeed,
that would just make me think even less likely that you're going to succeed the next time, because I think you have already used up all your luck. So you have more severe underestimation. So an individual with such a type of belief, essentially they believe in mean reversion, right? If you succeed this time, you are more likely to fail the next time. If return is high today, it's more likely to be low tomorrow. Second, because the law of small number investor believes that the sample distributions resemble the population distribution, in the short, so this is what I just talked about. In the short run, he expects mean reversion. Do we see that? Do we see that people expect mean reversion? So Hopper et al. 2008, it's a lab experiment, 6 sessions of training subjects each. The experiment involves subjects buying one risky asset and one risk-free asset, and subjects were told that the risky asset is a random walk. Okay, so what do you see? What do you see here? Now, the horizontal axis is how many number of same side have appeared on a coin toss, right? So the coin toss hasn't happened before. The coin toss is different from the previous one. The coin toss is exactly the same as the previous one, but not the one before. You have a free coin, just three same outcome in a row, four same outcome in a row, and so on, right? So the coins become more and more. So the coins become a longer and longer straight. And I believe the number is the ratio allocated to the risky asset. Number allocated to risky asset. So now, before there's actually any long series of same outcomes, subjects are about 60% willing to invest in risky assets because risky assets has higher return, right? So they put mostly in stock, right? But as you get high outcome continuously, then the subjects were less and less likely to invest in stock. So that's a belief in mean reversion, right? Even though they were told that it's a random walk. But somehow they just decided they're not going to invest in the risky asset anymore. So that's not a correct understanding of random walk. So clearly people believe in mean reversion even if they were explicitly told that it's a random walk. So if you think about this realistically, it's a bit hard not to sympathize with people in these experiments. So think about stock market, right? When the stock market, so if you hold a stock, and the stock went up by a lot in the past week, it went up every single day. It seems natural that just to worry about it go back down. It's just natural, right? Good. Next. Now, what will the investor infer from 2 successful years in a row by a particular manager? To understand that, we need to use the Bayes rule. base rule states that the probability of x given y equals to the probability of y given x times the probability of x over all possible scenarios summed together that involves y. Now, in English, that means how likely is x given y equals to how likely is y given x times how likely is x over how likely is y overall. So in our case, the x would be manager of a particular type, and y would be 2 successful years in a row.
Right. So what does it say? So let's say x is the type of the manager. Y is 2 successful years in a row. So the chance that the manager is a good manager, given that he has 2 successful years in a row, equals to the chance that a good manager can get 2 successful years in a row, multiplied by what I think the chance of getting a good manager is, over the chance of everything happening summed together. Right? So that would be base rule. Okay.
So in our case, we have three numbers we have to calculate. The chance of a good manager given 2 success, right? The chance of a average manager given 2 success, and the chance of a bad manager given 2 success. And by base rule, this calculation would be, okay, so what's the chance that a good manager would get 2 success in a row? So that's, as we know, 3/4 square, because it's independent, and 2 years in a row, that would be 3/4 times 3/4. What's the chance that a good manager happens? Now, since we're talking about we're just observing what's happening, this has to be based on our PIRA. So we think there's going to be 1/3 chance that we see a good manager in any given situation. So this would be 1/3 divided by all the stuff below. Now, let me write down the stuff at the top first before I actually write down the stuff at the bottom, because the stuff at the bottom is going to be the same for all 3 calculations. So what about an average manager? An average manager has half chance of succeeding. So in 2 years, that's half chance squared. Once again, we believe there's a 1/3 chance we're going to see an average manager, so we have to multiply that. And for bad manager, we think he only has 1/4 chance of succeeding squared, and there's 1/3 chance we're going to see one, so that's what we get. Now, what about the stuff at the bottom? The stuff at the bottom is simply the stuff at the top added together, because that's the only 3 possibilities in our case. So we add them up. 3/4 square, 1/3 plus half square, 1/3 plus 1/4 square, 1/3. Right. So that's what you have at the in the bottom. So it's the same for the rest of the ones, right? So it's okay. So you can fill them in very quickly. Right, and for these complicated numbers, you can simplify it out. I already have the answer, so I save you some time. It's 9/14 for the top one, 14/64 for the second one, and it's the third one is something what? It's 14 over. It's very. The third one is actually very small. The third one is actually very small. So the actually the 1/3 actually cancel out, right? So you get 1/16 at the top. Then you add up all the numbers in the bottom. Is actually what it is. So let me calculate. It's 9/16 plus 9/16 plus 4/16 plus 1/16. So it's 9 plus 4 plus 1. So that's 13, right? 9 plus 4, no, that's 14. That's 14/16, and at the top you have 1/16, so that's equals to 1/14. Yeah, I think. Yeah. So you can punch the calculator to make sure I calculate correctly, but I think that's about the right magnitude. Yeah, just not too sure about the one in the middle. So that's 9/14, 1/14 add together is 4/14. So the remaining one should be 4 out of 14. So yeah, so let's just make sure I actually calculate correctly. So the bottom is always the same. The bottom is always 14/16. The top here you have 1/4, so that's 4 out of 16. So you have 4 out of 14. Does that? Yeah, I'm not sure that actually goes out to. So I think this is 4 out of 14, and that adds up to 14. So that's right. Yeah. Okay. So these are objective calculations based on our Pyra. If we believe that each type have 1/3 chance of happening in random, and then we observe 2 success in a row, naturally we should assign more weight towards the types that have higher chance of giving us 2 success in a row. So we should put more weights that the current manager we are seeing is a good manager, since good managers have more chance of giving us 2 success in a row. So as you see, the probabilities have tilted much in favor of good managers, right? That's a lot higher than 1/3. 14 out of 9. That's almost 2/3 chance. And we have moved away from the bad managers because we understand that bad managers have very unlikely chance of giving us 2 success in a row. It's not 0, so we're still putting him here because we know that there is a small chance that it could be a bad manager, but we understand that most likely it's going to be a good manager. What about a believer in law of small numbers? Now, in the law of small numbers, what he believes is a bit different. So, what he estimated is the chance of a good manager after 2 successful years. So once again, we can calculate out the numbers in the top before we sum them up at the bottom. So he believes that, okay, so for such a manager, the first time, yes, he has a 3/4 chance of succeeding. The next time, he only has 2/3 chance of succeeding, and multiplied by 1/3, which is the chance which is the Pyra. What about an average manager? The average manager has half chance of succeeding, but the next time he used up one of his luck, so he only have 1/3 chance of succeeding. We are assuming that everyone has two chance of succeeding and 2 chance of failing at this moment. We talk about what happens if you have more chance for like 5 chances of succeeding, 5 chances of failing later on. So for now, we are assuming that there are 2 chances of succeeding, 2 chances of failing, right? Like this. Succeed, succeed, fail, fail. Finally, for the bad manager, he only has a 1/4 chance of succeeding to begin with, so the next round he actually has no chance. And the pyro is 1/3 chance we're going to meet such a manager. And then you sum up all these numbers at the bottom. So 3/4, 2/3, 1/3, plus 1/2, 1/3, 1/3. We don't need to add up the one from the bad manager because we know it's going to be 0. So this is 0. We already know. No need to calculate, since there's a 0 in the middle. The other ones, if you cancel things out, you get, I think, 3/4 times 2/3, 3/4, so that's 6 over 12. And then the other ones, you have 6 over 12 plus 2 over 12, that's 5 over, right, that's 6 over 12, 2 over 12, 9 over 12, right, math is hard, 6, 2, no, 6, 2 is 8, 8 over 12, so 2 over, that's over 12, so you have what, 3/4 chance, and this is 1/4 chance, all right, I think this is right. Okay, so I think the math is correct. The difference between the 2 types are, well, the difference between the 2 types is, a full Bayesian would correctly apply IID draws to the chance of succeeding. But the law of small number believer believe that the chance is actually of succeeding goes down as you succeed more often. So that's the difference between the 2. And with that, what do you see? While a Bayesian would rationally tilt the evidence towards the good manager because it has a higher chance of succeeding, after all, the believer law of small number do that even more than the Bayesian, right? In the OSN believer's mind, there's actually 3/4 chance of the manager being a good one, only 1/4 chance of being an average one, whereas previously it's more like 1/3 chance, right? And there's actually no chance the manager is going to be a bad one, because he doesn't believe that a bad manager can succeed 2 years in a row. So what you observe here is sorry, this is smaller. This and this is also smaller. So there is essentially a polarization of belief. Or you can say it's a rush to judgment. The LSN believer believes that she can draw pretty much the conclusion from 2 observations. So she's in some sense, she's a lot more confident about the type of manager she's observing than a true Bayesian. The Bayesian would say, well, there's still some chance that this is actually a bad manager, But for the law of small number believer, no, there's no chance that bad manager never succeed twice in a row. And actually, it's unlikely it's going to be an average manager because average managers are unlikely to succeed twice in a row too. So I'm pretty sure it's going to be a good manager. So the estimated likelihood of a particular type is skewed towards the type that has the most chance of resembling the outcome. Right? Good managers have the most chance of generating two success, so the LSM believer put too much weight into that type. Now, what if this is completely generated by the fact that the law of small number believer believes that success and failure are drawn from limited number of each. What if you increase number? Instead of having just SSFF, and what if you have something like SSSSSFFFFF? Oops. Okay, here's the part I have to be very careful, since if I go back, it would. What happens when a law of small number believer faces small sample from multiple sources? For example, there are hundreds of mutual funds and analysts, but the number of observations for each of them is small. For a new fund, you might have just a few months of data. Even for a well-established fund, let's say for 10 years, you have 10 annual observations, 120 monthly observations, which is still not a lot in terms of finance research. For trackability, we'll consider a case where there are an infinite number of sources. This allows us to use a ratio to represent the numbers of mutual funds or analysts. There are three types of managers. Probability of performing well equals to 0, 0.5, and 1 respectively. Notice that we have simplified things by assuming that bad managers always do poorly and that good managers always do well. The true probability of bad managers equals to the probability of good managers equals to Q. Once again, this allows us to simplify things down to a single number Q. Q has to be smaller than or equal to half because, well, half bad, half good equals to 1, which is 100% already. The chance of seeing an average manager then is 1 minus 2Q. Finally, we allow the law of small number believers believe to be incorrect. So her perceived chance of seeing a bad manager equals to Q tutor. All right. So I've actually calculated the number. I've already calculated the number and draw a line. But let me show you how this is actually calculated. All right, how this is actually calculated. Now remember that the average manager have half chance of success in any given year. So in 2 years, that would be 1 quarter, right? Right, 1 quarter. So here we go. I'm going to use. That would equal to. Now the bad manager has no chance of succeeding 2 years in a row. So for them, remember there are Q of them, they never succeed. So they're not contributing to this chance of seeing 2 good years. We have 1 minus 2Q good average managers, and they have 1 quarter chance of succeeding 2 years in a row. So these are average. And finally, the good managers always succeed. So with these numbers, so what would you get? So the actual probability that you will see two good years in a row, given that there are Q bad managers and Q good managers, equals to, so I'm just going to write it here in the front, okay? If you just add up all the numbers, right? 1/4 minus 1/2 Q plus Q, so that's 1/4 plus 1/2 Q. Okay? What about law of small number believer? All right. So I'm going to add a tutor on the top of probability just to indicate that this is what he thinks. What he thinks is that, okay, once again, bad managers have no chance of succeeding, that we know. The average manager, remember, does not have 1/4 chance of getting 2 good years in a row because he doesn't believe in IID. He believes in negative serial correlation. So that's half chance in his first year and goes down to 1/3 in the second year, just like before. And for the good manager, now this case is still 1 because, just to make it clear, initially it's 4/4, then it's 3/3, right? So it's still 1. It goes from 4/4 to 3/3. And if you calculate this number out, it is 1/6 plus 2/3 Q tutor. So 1/6 plus 2/3 Q tutor. The interesting part is what happens when the law of small number believer trying to infer Q tutor from actual data. So in trying to do an inference, right? So he would naturally be equating what he believes is going to happen with what actually happened, right? In his mind. This is the data generating process, right? On the left. He believes this is the data generating process. And this is on the right hand side what he observed. So naturally he is going to equate the two and it's going to infer Q tutor. Now remember, the law of small number believer doesn't know Q. He only knows the number. This is a number to him. So he's going to infer Q tutor from this number. So you rearrange, right? Move the 1/6 over to the other side, multiply both sides by 3, divide both sides by 2. You get Q tutor equals to 1/8 plus 3/4 Q, which is the line I drew here. What does it say? What does it say? The first thing you notice is, even if Q is 0, Q tutor is still positive. What does that mean? Even, so remember Q is the ratio of good managers, and it's also the ratio of bad managers. What this says is even if there's no good bad managers, no bad managers, so there are only average managers. Everyone is doing things by chance. The law of small number believer is still going to infer that there are good managers and bad managers. In other words, he's over-reading the data. He's over-reading. He's trying to interpret too much out of the data. What happened by chance? He interprets as observation of true ability. Right? He doesn't believe that someone can fail 2 years in a row. Sorry, that's not true. Correct. So he doesn't believe that bad managers can fail 2 years in a row. And as we calculated before, he attributes too much weight on the good managers. So he over-inferred. Things couldn't happen by chance. So it must be actual ability. So he's going to believe there are good managers. He's going to believe there are good managers even when they're not, and he's going to believe there are bad managers even when they're not. Okay, that's the first observation. Second, the slope is less than 1. Now, if you think about it, this has to be the case, right? This has to be the case because you need, in the case that there are only good managers and bad managers and no average managers, right? So Q equals to 0.5. Q equals to 0.5. So what do you have here? 0.5. So that's 1/2. 1/2 times 3/4 is 3/8 plus 1/8. That's added together is 1/2 again, right? You can't break the law of probabilities even if you have incorrect beliefs. Q tilde cannot be bigger than 1/2. Since you have Q tilde represents both the ratio of good managers and the ratio of bad managers, they can at most be half. That the law of small number believer does know. For that reason, his inference cannot go up by 1 here. It cannot be 1. Otherwise, you would have the weird case where if there are actually half-half, you would actually get an inference that's bigger than half. That's not correct. Right? So the most important point is this individual would observe ability when there is none. And you can push this one step further and ask, what happens if this individual choose whom to invest with by his inference, right? You have all these mutual funds out there. You have to choose a few to invest with. And what happens if he constantly makes inference about the fund's ability from short samples of data and alter his investments? Okay, so now this is from the New York Times. I think this diagram is very informative. How many mutual funds routinely rout the market? The answer is, depends on how long you look. If you look long enough, 0, none. So if you just look at a short duration, like a year, right? Then you have a lot of funds outperforming the market, right? If anything, right? If you assume the market is all made up of mutual funds, then by chance you would have half of them outperforming the others, right? By asset, half of them would outperform the others. And if there's true ability, then you would observe a continuous series of funds outperforming the market. But if it's by random chance, eventually you would see them all weed out, right? The chance that a fund outperform a market in a year is 1/2, but then the next year is 1/4, then the year after is 1/8, 1/16, 1/32, and so on, right? It goes down very quickly. That's the nice thing about exponential increase. Just goes down very quickly. And basically in 1, 2, 3, 4, 5, 6 years, you get none. No mutual funds in the market manage to outperform the market 5 to 6 years. Well, I mean, now, I think what is there are some there's some concerns on how you actually measure things like that and so this is mutual funds, right? Hedge fund is different. Is a different category. So there are some would say there are some hedge funds that actually manage to beat the market, like for over a decade. But anyway, it's a very small number. Like out of hundreds, thousands of funds on the market, a few, like in the single digit, might outperform the market as long as 5 to 6 years in a row. So it's a very small number. Okay, so this is the actual excerpt from the article. Does past performance matter? Blah, 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 blah. So, okay. So 2,862 broad actively managed domestic stock. Now it's very important. It does not include passive index funds, right? Passive. If you invest in a passive index fund, remember what we have learned about small stocks and value stocks, right? A small stock fund is going to outperform the market naturally because we know they have higher beta. Right? And there's a small minus big effect. Right? So it only includes actively managed stock mutual funds that were in operation for the 12 months through 2010. So that's where they started. I think what it means is they were in operation for the 12 months. Yeah, so they were already in existence for the whole year in 2010, right? So then it's actually calculated by S&P Dow Jones. So they calculate the performance every year. Select the 25% of the funds with the best return over those 12 months, and ask how many of those funds actually remain in top quarter in each of the 4 succeeding 12-month period through March 2014, right? So in this case, their criterion for being a good fund is the same as what we did in our calculation, right? 1/4. One quarter. The cutoff is 1/4. The best 1/4. Let's look at what happens to that, right? So out of the 2,862, 2 were left in 6 years. Right? So this is where the traditional investment advice of past performance does not guarantee future performance makes a lot of sense. Right? So I think the symbol, I want to type Q, but then I type beta. But I think this should be Q. Somehow I'll type beta. Okay, so a law of small number believer exaggerates how common extreme types are. Now let's think about this. So as we just calculated, he would believe that there are more good types and bad types than there actually are, right? Even if there are none, then he would still believe there are some, right? And as we explained, that's because he doesn't really believe extreme outcomes can happen by chance. He thinks that extreme outcome has to be caused by extreme types. And this exaggeration increases with the fraction of average managers there are, right? Because if there are no average manager, that's one end, right? If there are actually no average manager, there's no exaggeration. He correctly infers that there are half good types, half bad types. There are no average types. So he actually will be correct. Even with his wrong inference, he's still correct, because he cannot be more wrong than the reality. But when there are only average managers, then he's really wrong, because it infers that there are 1/8 good types and 1/8 bad types. That's the diagram we saw. What's interesting is if you use the inference as the pyra in for next stage inference, right? Your pyra will be more dispersed than the true distribution. This would skew your inference even further, right? If you the way Bayes' rule works is, right? You're tilting your estimates towards what's most likely, right? And when your pyra is already rarely biased towards what you think is the most likely case, it's going to go even more extreme. Eventually, basically rule out all other possibilities. Now, it would be of practical interest to think about this too. What happens if a law of small number believer choose whom he invests with based on observed outcome, right? And it's very intuitive. Okay, so I'm going to look at a few funds. I'm going to invest with the good ones I see, right? So I invest in some of the good funds. Then every year or two, I'm going to review their performance. I'm going to stop investing in the bad ones and keep investing in the good ones. So that's a very intuitive strategy. It sounds very reasonable. And keep investing with the good ones. Stop investing with the bad ones. Now, we're going to suppose that the investor only observed the performance of managers he invests with. I think it's a reasonable assumption, given that attention is limited, right? And if you think about, well, you don't have MPF, I do, right? MPF, so in MPF, you are investing in your retirement in Hong Kong, you're investing your retirement savings in a number of funds available to you, right? You receive a report once a year on the returns and performance and composition of the funds. But you only get it from the companies with the company you're investing, right? You don't actually know the performance of other companies unless you actively go online and look for the information, which is public. But I'm pretty sure most people don't do that. So I think it's a reasonable assumption that people don't pay attention to funds that they don't invest with. We're talking about the average investor, not talking about really sophisticated ones. So we're going to assume further that all managers are average, generating good performance half the time. So this is what we just calculated. No good managers, no bad managers, only average types. Right. Remember, there's over-inferencing, right? So the investor do believe that there are good managers. even if they're not in the reality, so he still believes there are good managers. So he will pick the good ones because he believes they are good ones. The good ones, by definition, is the ones that perform well multiple times in a row. So he will believe. So that's his definition of good ones because he over-inferred. He stay with the good ones. But what happens with the good ones? Well, what he thinks are the good ones really only exist by chance, right? So eventually, law of large number kicks in, right? So you have a fund that performed well 2 years in a row. Next month, next month only half a chance of performing performing well, right? So that reduced number of funds by half. Another month, another half. Another month, another half. Eventually, the number would dwindle to a very small number. So eventually, there will be no good funds among the ones that he initially invested with. And if the investor do not actively seek out new funds, right? Let's just say you just look at the fixed pool of funds. You just look at the fixed pool of funds. He doesn't seek out new funds. You observe that, well, you just observe what he invests in, and he will be disappointed. Whatever he thinks is good eventually turns out to be average, right? And whatever appears to be bad, he simply discard them very early on. So he does not realize that what he thinks is bad will come back up by law of small numbers. That's why by law of large numbers. Okay. So the average performance is going to be below half. Curiously. And moreover, it reinforced his belief that you have to shop around. Right? You have to shop around, if only to avoid the bad ones. If only to avoid the bad ones. So you can see that despite that there are good arguments that funds pretty much perform like the market over time, right? As we saw in the news article just now. Even though we have evidence of that, people probably won't believe in that. For most people, based on what they see in the market, they would think that there are value to shopping around. Okay, so I think this is where the law of small number article. Actually, I have one more. So this is actually, yeah, interesting. So this is the same study as the one that I shown you at the beginning of today, right? The one where you are supposed to bet on the side of a coin based on how many times you have seen the same side of the coin. Now, this experiment has a second part, which is very interesting, is that the 5 expert opinions were provided. Remember, they were told that these were random walks. And then in the experiment, they were also provided with these expert opinions that claim to be able to predict the outcome. Now, if you truly understand the experimental instruction, then you know that these would be bullshit, right? I mean, a random walk with expert opinion. Okay, but this is the exact terms that were used in the instruction. There are 5 experts in the market who claim that they are able to predict the market development better than the majority of all market participants. Okay. Now this diagram shows what happens. So the subjects have to select an expert, right? So the horizontal axis is how many times the expert has guessed correctly. And remember, these are by chance. These are really by chance. Right? By chance, there will be some expert that gets correctly. So how likely? So this is how many times the expert has guessed the result correctly. It's by chance. The vertical axis is how the proportion of subjects who stayed with the expert. I think that means that they actually basically kind of like they select the expert to invest for them. I think that's what it means here. So when you select an expert, you are committing to bet on the expert's recommendation. So now for losing expert, right? Basically no one thinks in, right? 3%, right? Very good, less than 3%. But if the expert gets correctly, right? Gets in 1 time, 2 times, 3 times, 4 times, 5 times, more and more people would choose to bet with the expert. If the expert actually managed to get 5 times correct in a row, over 60% of the subjects would choose that expert. So, yeah, the question is, did the subject not understand the concept of random walk, even when it was explained in plain terms? Right? They were told, they were explained what a random walk is. And yet they still do this. Now you can try to explain it, right? One is they truly do not understand what random walk is, right? They kind of understand random walk as in something that should balance out, yet still predictable. That might be the case. Another possibility is that they might think that the experiment is rigged, right? So you don't believe what the experimental instructions tells you. You think that it is actually a biased experiment, a biased coin. So the expert truly knows something. The experts are not human. The experts are just computer randomly generating numbers. But they were just called experts. So all the subjects know is the prediction. So they might think that the expert is some process that actually understands the underlying bias coin. Right? Now in the economic experiment, we have a very strong norm of not deceiving subjects. Typically in economic experiments, what we say in the instructions are true, right? When we say it's a random walk, it's truly a random walk, right? Because we precisely want to avoid the possibility that the subjects do not believe in your instructions. When you say it's a random walk, they believe it's not a random walk, then your experiment is toast, right? So for that reason, as a discipline, economic experiments overwhelmingly overwhelmingly truth-telling. We do not engage in deception. This is different from some psychology experiment, like some of the very famous experiments, Milgram experiment, the Stanford Prison experiment. These involve deception. Some of them involve deception. So the prison experiment involves deception in the sense that they actually send police to arrest the participating students and bring them to the basement of the Stanford psychology department in a makeshift prison. So it's deception to the outside world, right? Because they were truly arrested by a police car, by a uniformed policeman. For the electric shock experiment, I think I mentioned that earlier on, right? You came in an experiment. I'm the experimenter. You see another person in the other room. You can communicate, and I ask you to press a button to shock, to send electric shock to him. And I ask you to send increasingly deadly electric shock, right? So that's deception, because first, no shock was ever sent. I mean, I'm not sure actually no shock, but definitely no harmful shock was ever sent. The person in the other room was an actor. Now that's complete deception, right? That's complete deception. In economics, we don't do that. So we try very hard to rule out the possibility that it's due to the distrust of experimental instructions. Okay. I think I'll still say a more natural interpretation is people just disregard what you say about the data generating process. They just believe in their eyes. When they see someone or something that can predict the future outcome a few times in a row, they believe that it has value.